The word partition, unfortunately, is used two different ways in combinatorics. There's partitions of sets and partitions of integers. An integer partition is a weakly decreasing strong composition. Of an integer. So we have lambda with, let's say, r components. And since this is a strong composition of an integer, say n, we've got the sum of these components equal to n. We write lambda, this thing is v dash in LaTeX. Lambda v dash n for lambda is a partition of n. Also, it's convenient to write lambda in absolute value, so the size of lambda is n, if lambda is a partition of n. If we need to refer to the number of non-zero components of lambda, we write L of lambda, so that's r in this case. And these components are called parts. So for example, if we list some integers and partitions of those integers, since these components are all positive, the only partition of 0 is the empty partition. The only partition of 1 is 1. There are two partitions of 2. We have 2 and 1, 1. All right, let me erase these and put partitions of 3 and 4 here. The partitions of 3 are the partition into one part, 3, the partition into two parts, 2, 1, and the partition into three parts, 1, 1, 1. The partitions of 4 are the partition into one part, and then we've got two different partitions into two parts. 3, 1, and 2, 2. And then also 2, 1, 1, and 1, 1, 1, 1. So there's 5 different partitions of 4. A useful way to organize the partitions of n is to write them in a poset called the dominance order or majorization order. We define the dominance or majorization order on partitions of n by declaring that lambda is less than or equal to mu if each of the partial orders of lambda is less than or equal to the corresponding partial order of mu. Each of the partial sums of lambda is less than or equal to the corresponding partial sum of mu. So if lambda 1 is less than or equal to mu 1, lambda 1 plus lambda 2 is less than or equal to mu 1 plus mu 2, etc. Now if we get past the smallest part, say one of these partitions has more parts than the other, so we can't technically compare the corresponding partial sums, but we can just add zeros to the smaller one. So if we get past the smallest part of the shorter partition, then we pad it with zeros. To continue comparing something like lambda 1 up to lambda I less than or equal to mu 1 up to mu I. So let's do this for n equals 6. So let's list the partitions first and then we'll order them in the poset. So we have 6 for the 2-part partitions. We've got 5, 1, 4, 2, 3, 3. Then for the 3-part partitions, we have 4, 1, 1, 3, 2, 1, 2, 2, 2. For the 4-part partitions, I guess we can't start with 4. 3, 1, 1, 1, 2, 2, 1, 1, and then the 5-part partitions, I guess, is just 2, 1, 1, 1. Oh wait, yes, 2, 1, 1, 1, and then there's a single. No, that's 5. 4 parts. So for a 5-part partition, 2, okay, and 4 ones. And then the single 6-part partition would be 6 ones. The greatest partition in the dominance order is always the single part partition, because if we compare partial sums of that with anything else, 6 is bigger than 5 or 4 or 3 or anything else, then 6 plus 0 is certainly going to be at least as big as the first 2 terms of any other partition, etc. So the partial sums here are never going to lose to the partial sums of another partition. Then 5, 1 is next. Then 4, 2. The partial sums here are 5 versus 4 and 6 versus 6. So 5, 1 wins the 5 versus 4 contest, and then they tie 6 versus 6. Alright, so now the first interesting thing happens. We have 4, 1, 1 and 3, 3. So these are both less than 4, 2, because if we look at partial sums, 4 is greater than 3. And then 6 equals 6. Here, 4 equals 4, but then 6 is greater than 5. We look at the second partial sum. Then the third partial sum, we put a 0 there just to make it possible, and 6 compares to 6. So since we have tie and win, 4, 2 goes above 4, 1, 1. Since we have win and tie, 4, 2 goes above 3, 3. But I claim that neither one of these goes above the other. Because if we look at 4, 1, 1 versus 3, 3, The partial sums are 4, which is a win for 4, 1, 1. And then 4 plus 1 is 5, and 3 plus 3 is 6, which is a win for 3, 3. So since 4, 1, 1 won one of the contests, and 3, 3 won the other one, neither of them is greater than the other, so they're incomparable here. Then 3, 2, 1 is less than both of these, because the partial sums are 3 versus 3, 6 versus 5. That one's greater. And here 4 versus 3, 5 versus 5 is a tie, and 6 versus 6. So the first one, 4 versus 3, makes that element greater. And then we've got something interesting again. 3, 1, 1, 1, and 2, 2, 2 are incomparable, but they're less than 3, 2, 1. 3 is greater than 2, 5 is greater than 4, and then 6 ties 6. So that one's bigger than 2, 2, 2. Here, 3 ties 3. But then 3, 2 is 5, which is greater than 3, 1, which is 4. And then 6 is greater than 5. So this one wins any competition where they get a different answer. And then after that, we've got 2, 2, 1, 1, 2, 1, 1, 1, 1, and 6 ones. So this is the dominance order or majorization order on partitions of 6. Now, one convenient way to picture a partition is to use dots to represent the integers. So we define the Ferrer's diagram of lambda by drawing lambda 1 dots, lambda 2 dots, etc. So the Ferrer's diagram of 3, 1, 1, 1 would be 3 dots, 1 dot, 1 dot, 1 dot. Now, some people start at the bottom and put successive dots above, and some people start at the top and put successive dots below. So I guess we could have also written 3 dots, 1 dot, 1 dot, 1 dot, also to represent the 3, 1, 1, 1. This convention with the largest part on top is called English notation. And this notation with the largest number of dots on the bottom is called French notation. Typically, if you live in an English-speaking country, you use the English notation. And if you live in a French-speaking country, you use the French notation. Unless you got your PhD at UCSD in California, in which case you use the French notation. Now, even though I studied on the East Coast, I actually use the French notation more often. But we'll use both. Now, related to the Ferrer's diagram is something called a Young diagram. We define the Young diagram of lambda by drawing lambda 1 boxes instead of dots, lambda 2 boxes instead of dots, etc. So for 3, 1, 1, 1, that would look like 3 boxes, 1 box, 1 box, 1 box in English notation, and 3 boxes, 1 box, 1 box, 1 box in French notation. So almost exactly the same thing, but the Young diagram has boxes where you could write things in the boxes if it's ever convenient to arrange things in a table of this shape. And we will do that, so we will be using Young diagrams probably more often than Ferris diagrams, but they're the same thing, essentially. Now you might notice that this poset looks the same upside down as it does right side up. That is, it's isomorphic to its dual, dual being the upside down version of the poset. And the relationship between partitions that are down here with their partners that are up there is, well, if I draw it, maybe it'll be obvious. So 6 ones looks like that in a Young diagram, and 6, I'm sorry, that's 6. 6 ones would be vertical. 1, 1, 1, 1, 1, 1. And then 6 is horizontal. Let me do 5, 1 also. So 5, 1, I'll do this in French notation. It has 5 boxes and then 1. And then 2 and 4 ones has French notation, 2 boxes and 4 stacked boxes above it. The connection is that if you reflect these diagrams in the line y equals x, imagine that the origin is down here, that map takes an element near the bottom of the poset to an element near the top of the poset. That actually describes exactly what happens when we turn this upside down. And this reflecting operation is called transposing or conjugating. So given partition lambda, we define lambda transpose, or some people write lambda prime, to be the partition whose French diagram, Young diagram or Ferris diagram, it doesn't matter, reflects in the line y equals x to make the diagram of lambda. So we have 6 transpose equals 1, 1, 1, 1, 1, 1. 5, 1 transpose equals 2, 1, 1, 1, 1. Another way you could think about the transpose partition is that you count boxes in columns rather than in rows. So 3, 1, 1, 1 transpose would be 4, 1, 1. 4, 1, 1 transpose equals 3, 1, 1, 1. 4, 2 transpose is 2, 2, 1, 1. 3, 3 transpose equals 2, 2, 2. 3, 2, 1 transposes itself. And then I guess we have everything, because each of these partitions has come as a transpose of something we've seen before, and the transpose of a partition is just the original partition. Now the proof that transposing partitions flips this both set upside down and self-dual is something that we do in Math 305, and I think that we won't actually need that in this course, so I think I'm going to skip it. Now, an obvious question to ask is, how many partitions of an integer are there? Because we've asked about how many k-element subsets, how many k-element multisets, how many set partitions, and it turns out that once again there's no nice formula for the number of partitions of an integer. We do have a generating function though. So let's write out 1 over 1 minus x1z times 1 over 1 minus x2z squared times 1 over 1 minus x3 z cubed, etc. So this will be an infinite product. So each of these we can expand as a power series by thinking of it as a geometric series. So this is 1 plus x1z plus x1 squared z squared. For convenience, I'm going to write x1 z squared. And then x1 cubed z cubed. For convenience, again, I'm going to write x1 z cubed, etc. times 1 plus x2 z squared plus x2 squared z squared squared. For convenience, I'm going to write x2 z to the fourth. And here again, I'm sorry, next term. For convenience, I'll write x2 for x2 cubed, and z to the sixth. And then for the third fraction here, we have 1 plus x3 z cubed plus x3 z to the sixth plus x3 z to the ninth, etc. Maybe that's enough factors here to get us going. So the constant term is 1, because the only way to get 1 is to take 1 from every single factor. And then if we want a single z, the single z is only going to come from this first factor, because everywhere else the powers of z are too high. So 1 plus x1z. And now we've got two ways to get a z squared. We can either take a z squared from the first factor and then 1's everywhere else, or a z squared from the second factor and 1's everywhere else. The z squared from the first factor has x1 next to it. And the z squared from the second factor has x2. Now how can we get a z cubed? We get a z cubed from the first factor, or a z cubed from the second factor, or we can take a z squared and a z to the first. Well, the z first only appears here, and then we'll use this z squared. And then the coefficients in those three cases are x1, 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 x2, x1, and x3. And if you can think about it, you can see that the coefficient of z to the k is going to be a sum of products of x's whose indices give us precisely the partitions of k. So the coefficient is essentially a list of partitions of k. Now if we set all of the x's here equal to 1, then every one of these monomials which represents a partition is going to contribute 1, and then we'll simply count the number of partitions. So that means that if we take the product as I goes from 1 to infinity of 1 over 1 minus z to the I, so 1 over 1 minus z times 1 over 1 minus z squared times 1 over 1 minus z cubed, etc. That gives us a sum as n goes from 0 to infinity of, let's say, Pn z to the n, where Pn is the number of partitions of the integer n. The end.